So reactants change into products. That's what's happening during our chemical reaction, right? And some factors that affect how quickly that occurs, Michelle found them on the back of those notes, and those are the things that we need to go over today before you try to get the elephant toothpaste to touch the ceiling. Because the objective is to get the reaction of the hydrogen peroxide to happen as quickly as possible. That way it shoots up into the air really fast, right? Because we looked at the two different examples with the one that happened pretty fast and the one that just took a long time to go, right? That one won't reach the ceiling, right? So what's happening is your reactants are going to products, right? And we graphed those changes over time on Friday. So you start with the concentration of reactants, and those actually decrease, right? So you can see how the reactants or the reagents decrease over time, and the products actually increase over time. So the steeper that slope, the quicker that reaction occurs, right? So think about sledding. If you're going down a hill that's steeper, that means the reaction is happening faster. You are sledding faster. So the reactants are changing into products faster at the beginning of our reaction than it is at the end. By the end of our reaction, there is no slope, and you have basically stopped changing reactants into products, right? And that's what it means that your reaction has slowed down or stopped, right? Okay, then we looked at an example of how a reaction actually occurs on the molecular level. What is happening to those molecules in order to change? So you have your beginning reactants. We've got BRNO. That's the substance, that's the reactant. And it's a bromine bonded to a nitrogen bonded to an oxygen. So if that is our starting material, something has to happen to it to change it, right? So what happens is a collision. You have to have a collision with enough energy in the right orientation in order to break and then make new bonds. So you can see that this dotted line right here is referring to the fact that bromine and nitrogen have broken that bond. They are not connected anymore when they were connected over here, right?
No.
And then what's happening right here? What's happening right here? They're coming together. We're creating a new bond, right? So this is called our activated complex. You have bonds being broken and bonds being formed to make a new arrangement of those atoms into our products. And so now we have two separate products. We have NO and Br, too. Okay? So that's how our reactants change into products, through the breaking and the making of new bonds. Okay? And so over time, that changes. If you start at time 0, you only have reactants, right? So at the beginning, right here, we only have reactants with a certain amount of energy. Then we've got that activation energy barrier, right? And That's the minimum amount of energy to start a reaction. Which means you have to collide. There is energy that has to happen in order to change your reactants to your products. So, as that reaction progresses from reactants to products, it goes through a transition state. And that's really what this is right here. And this is where you need to pick up on these notes. This is where we left off on Friday. So find this spot in your notes, please. So transition state is what's happening right here. The reactants are transitioning into products. That's where the bonds are breaking and the bonds are forming. So the transition state and the activated complex are really the same thing. It's how the molecules are arranged at the top of that energy barrier right here. That's what they look like for that split second before they change into products. It doesn't last very long because this has a ton of energy. It's going to break apart. It's not going to stay like this very long because it's not very stable to have like half bonds in between, right? So at the end of a reaction, there are products with a certain amount of energy. That's how we finish up this reaction. We've got our products. Our activated complex has split into the final products. So we've gone through that whole graph here. We started with reactants. We went to our transition state where our activated complex was breaking and forming bonds, and then we ended up with products with a certain amount of energy. And so, if you remember, we talked about the delta H last unit. Delta E is the same thing. It's the change in energy. When we were talking about delta H, we were just talking about heat energy specifically. So delta H was talking about heat energy specifically. Delta E is talking about energy in general. Potential energy in the bonds of the molecules going to kinetic energy released to create those bonds that are formed. Okay? And so remember that energy change, the difference in energy from the reactants to the products, is always the distance from the energy level that you start with for the reactants to the energy level of the products. So it's this distance between reactants and products is how much your energy level is changing because of a reaction. Okay? And from last unit, we talked about exothermic and endothermic, and so this should be a review, but I want to make sure that you have these notes again because we're going to use them in this unit as well. So endothermic is the type of reaction that absorbs energy. So that means that the products have more energy than the reactants. So which one of these graphs demonstrates the products having more energy, being higher on the graph? So the products are at the end, right? So in which one of these graphs are the products higher than the reactants? Yeah, the first one. The one that's labeled endothermic. Right? So those products are higher than the reactants. Those products have more energy than the reactants did. And then exothermic is the opposite. That's the release of energy. So the products have less energy than the reactants. You're ending up with less energy than what you started with. Okay?
We have like one more week in this class. Oh, okay.
Think about that geometry grade I'm gonna have to bring up.
Yeah.
Okay, so now we get to the good stuff. This is the part that you want to pay special attention to so that you can get the elephant toothpaste to reach the ceiling. So these are the 4 things that affect the rate of a reaction, or how fast a reaction is going to occur. The first one is concentration. So concentration is the amount of a reactant that you have in a given space, right? It's how much is there of that reactant in the solution. And so today I have 2 different concentrations of our catalyst to use, our potassium iodide. Do you remember that from the other day? I have 2 molar and 4 molar potassium iodide. So when I say molar, I'm referring to moles per liter. So how many moles, how many molecules, in other words, are in a liter of that solution. So if I have 2 molar, that means I have 2 moles per liter. And if I have 4 molar, that means I have 4 moles per liter. Which one is more concentrated? The 4 molar. I have twice as many moles in the same volume. Right? So that would be like drawing a particle diagram that has that many particles per space versus that many particles per space, right? So this would kind of represent our 2 molar, and this would kind of represent our 4 molar. Does that make sense? Can you guys see that over there?
Yeah.
Okay, so concentration, the more concentrated something is, the more reactants you have to be able to react. The more reactions can take place at the same time, which would make it go faster, right? So as the concentration of reactants increases, there are more particles, so more collisions can happen, and that rate will increase. It'd be like all of you in here in the classroom, you're a little bit more spread out, right? You don't have to bump into one another very much, right? But if I take all of you and I squeeze you into my chemical closet, then
Where's that at?
you're going to be much more concentrated in that small space, and you're going to bump into one another a lot more, right? There's going to be a lot more reactions going on there, right? Might be getting upset with one another because you're bumping into one another, and that's a reaction that's happening, right? So that's how concentration affects the rate of a reaction. The next one is temperature. So as the temperature increases, the particles move faster, right? We looked at that last unit. The higher the temperature, the faster those molecules are moving. Well, if the molecules are moving faster, then they can collide with more energy, right? And you need energy for those collisions to actually cause breaking and making of new bonds. So the more energy you have, the more collisions you can have, and the more reactions can happen faster, right? What would happen to a reaction if I cooled it down?
It's gonna slow down.
It'll slow down or maybe not happen much at all. Okay. Okay. Next one is surface area. So this is kind of a strange concept. Surface area refers to the surface of an object, right? This book has essentially 6 surfaces, right? One on the top, one on the bottom, and one on each of the 4 sides. Okay? And so if a reaction is happening, don't worry, I'm not going to drop it. If a reaction is happening on the book, this is our reactant. If a reaction is happening on this book, on the surface of this book only, then there's only 6 places where that reaction can happen, right? But what if I take this book and I open it up and I break it down into all of its pages? How many surfaces do I have now?
A very large amount.
A lot of surfaces. And so if I look on, how many pages are in this textbook, 696. Okay, so that would be 696 surfaces for the reaction to take place.
It'd be double because there'd be one side and another.
Yeah, it would be double that too. Very good.
Smart fella.
So that would be like 200 times more reaction places to occur, right? So if you break something up into smaller pieces, that would be increasing the surface area of your reactant, okay? Tomorrow we're going to do a lab with Alka-Seltzer tablets. You guys know what Alka-Seltzer tablets are?
They're disgusting.
Yeah.
Great.
So we're going to do some experimenting with surface area. So if you leave that whole tablet, how many surfaces do you have?
Like 3 technically.
Yeah, kind of. Yeah, like 3 surfaces. If you break that tablet up into like 4 chunks, how many surfaces do you have?
A lot.
8.
Yeah, 12 maybe?
I don't know, 16.
Okay. So if you had 4 pieces and each one had 3 surfaces-ish,
Oh, yeah.
okay, then you'd have about 12 surfaces. So the more surfaces you have, the more places those reactions can take place, and the faster that reaction can happen. Because you can do it at 12 different places all at once, right? Instead of just 3. Does that kind of make sense? Okay, and then what I want you to notice about all of these relationships is that they're direct, meaning if I increase the concentration, I increase the rate of the reaction. If I increase the temperature, I increase the rate of the reaction. And if I increase the surface area, I increase the rate of the reaction. Okay? Alright, and then the last one is about the catalyst. And if you remember from our reaction on Friday, the catalyst was what we added to make the reaction happen, right? The potassium iodide? Very good. So there are usually special proteins in our bodies called enzymes that actually make the reactions happen. We have an enzyme in our body that breaks down hydrogen peroxide. Did you know that? So, especially, it's in your blood. It's called catalase. And if you get a wound and you put hydrogen peroxide on it, it will bubble, right? Because you have that catalyst in your blood breaking down the hydrogen peroxide. And you see those bubbles, right? So that's truly what's happening in our bodies all the time with all kinds of chemicals. Not just hydrogen peroxide, but sugar. We have an enzyme that breaks down sugar. We have an enzyme that breaks down fat so that our bodies can use those nutrients. Okay? So when we have a catalyst, what it does is it lowers the activation energy to provide a new pathway for the reaction to occur. So we have, the catalyzed reaction in red here. And notice that that change in energy, that activation energy bump is a lot lower. So what that means is you don't have to have as high of a temperature or as high of a concentration or as high of a surface area in order for the reaction to actually happen. You don't have to have as much energy to make it go, simply because you have that catalyst there to help it. Okay? So this is what it looks like for an endothermic reaction. It's still lowering the activation energy. It's making it easier for that reaction to occur. Okay? Alright, so on the observations from Friday's demonstration, that first paper you guys had out, I want you to go back and try to come up with a reason why there was a difference in the 3 graduated cylinders. For number 4 on that paper, why was there a difference between the 3 graduated cylinders that you observed? And then for number 5, why was the 10 milliliters of potassium iodide important for the reaction to occur? What do you think the potassium iodide is? And then number 6, can you answer any of your own questions that you came up with? Okay, so I'm going to give you a couple minutes to do that.